Oxidation and reduction. The chemistry behind material transformations in the world of chemistry. Changes are happening constantly, and one of the most fundamental principles driving these changes is oxidation reduction, or redox reactions. Thousands of years ago, our ancestors observed substances burning and transforming through fire. However, it wasn't until much later that we understood these transformations weren't just destruction but rather the result of specific chemical reactions. Oxidation and reduction are essential reactions that influence the flow of energy and alter material properties. Let's dive into the fascinating mechanisms and principles behind these reactions. 1. Overview of oxidation-reduction reactions. Oxidation-reduction reactions involve the transfer of electrons, leading to changes in the materials involved. One substance loses electrons and becomes oxidized, while another gains electrons and becomes reduced. This reaction plays a key role in both natural and artificial processes. From the burning of wood to the rusting of iron and even the energy generation within our bodies, oxidation and reduction can be observed all around us. The concept of oxidation reduction can be defined through the idea of oxidation states. Oxidation states indicate how many electrons an atom has lost or gained. An increase in the oxidation state indicates oxidation, while a decrease represents reduction. 2. Historical background of oxidation and reduction. The concepts of oxidation and reduction evolved alongside the development of chemistry. In the early 18th century, oxygen was recognized as the key element enabling combustion. Antoine Lavoisier introduced the term oxidation when he observed substances burning in the presence of oxygen. Over time, chemists discovered that redox reactions could occur without oxygen, expanding our understanding. Once chemists discovered electrons, they began to redefine oxidation and reduction as reactions involving the movement of electrons. This approach significantly advanced our understanding of fundamental chemical reactions. 3. Mechanism of oxidation-reduction reactions. The essence of redox reactions lies in electron transfer. Electrons move between an oxidizing agent and a reducing agent, which play distinct roles. Oxidizing agent, a substance that causes oxidation in another substance while itself undergoing reduction. Reducing agent, a substance that causes reduction in another substance while itself undergoing oxidation. A classic example is the rusting of iron. Iron oxidizes when it reacts with oxygen to form iron oxide. During this process, iron's oxidation state increases, while oxygen's oxidation state decreases. This can be expressed as 4 Fe plus 3O2 2 Fe 2O3. In this reaction, iron is oxidized, and oxygen is reduced. Changes in oxidation states reveal how electrons were transferred, helping us understand the reaction mechanism. 4. Types of oxidation-reduction reactions. Redox reactions manifest in various forms. Some common types include direct electron transfer reactions. In these reactions, metals and nonmetals form compounds by exchanging electrons. For instance, sodium and chlorine react to form sodium chloride, NaCl, through electron transfer. Redox cycles. In biology, living organisms rely on redox reactions for energy. Cellular respiration, for example, is a redox process where glucose is oxidized, oxygen is reduced, and energy is released, which organisms use. Redox titration. This method leverages redox reactions for chemical analysis, allowing scientists to determine the concentration of specific substances by measuring redox components in a sample. 5. Real-world examples of oxidation-reduction reactions. Redox reactions are all around us. Here are a few everyday examples. Batteries. Inside batteries, oxidation-reduction reactions enable electron flow, creating an electric current. In lithium-ion batteries, lithium ions move between electrodes, storing and releasing energy. Rust. When iron reacts with oxygen, it forms rust, a common example of oxidation. Rust prevention techniques are based on understanding and controlling these redox processes. Biological processes, both respiration and photosynthesis depend on redox reactions. In respiration, organisms obtain energy, while photosynthesis stores energy in plants. 6. Importance and applications of oxidation-reduction. Oxidation-reduction reactions are vital across chemistry, engineering, environmental science, and biology. Understanding these reactions is essential for addressing pollution, energy storage, and conversion. For instance, hydrogen fuel cells rely on hydrogen oxidation and oxygen reduction, producing electricity in the process. Redox reactions also govern energy flow in living organisms, making them fundamental to life itself. Modern technology leverages this principle to drive sustainable energy developments and numerous scientific applications. Oxidation reduction reactions are more than just material transformations. As electrons move and energy exchanges hands, these reactions embody the harmonious flow of nature. By understanding these principles, we can envision a future of improved technologies and sustainable energy. The next time you see a metal rusting or a spark igniting, remember the magic of oxidation and reduction at play. Oxidation reduction reactions are foundational to chemistry, as well as essential processes in nature and human activities.